Now, the thing about coordinate proofs is it's kind of handy because you can always get them. Remember in geometry, it was always kind of tricky. You had to kind of work from the back and go forward and know all the tricky steps and so forth. But I almost think coordinate proofs is more brute force because you're going to take all these geometry ideas and translate them into coordinate ideas in analytic geometry. So, proving line segments congruent. Let's help you focus here with the curtain. That's the curtain on the wrong page. Let's put the curtain up. There we go, there we go, there we go, there we go. Line segments congruent. That was a big part of geometry, wasn't it?
Yes.
Now distance formula, which is messier, isn't it?
Yes.
Because you got all that square roots and difference and so forth, distance formula. How about non-vertical lines parallel? To show lines were parallel, you had that PCA and CAP and all that stuff. You'd have to come up with some kind of angles. Now you've got same slope. Perpendicular?
Opposite reciprocal.
Negative reciprocal slope. Remember what it was in geometry? In geometry, it's something else, right?
Perpendicular.
And then, how do you prove segments bisect each other in geometry?
The angle bisectors.
No, not the angle bisectors theorem.
Midpoint.
It's a midpoint if, and it bisects if it divides it into two congruent segments. Well, we have a nice midpoint formula for that, don't we?
Yes.
Yeah. Average of the x's, average of the y's.
Yes. Oh, that.
To show that lines are concurrent, you had to do all those liaison theorems, remember from geometry? Now you're just going to solve it algebraically and show that they have a common solution. Okay. So that's the idea behind that. So let's take a look at some of these examples. This first one, example 1, given the angle C is a right angle, M is the midpoint of AB, prove MC equals MA. And I've got it here as a thing I pasted from before. But let's actually look at it in a GeoGebra so you can see what I mean by a dynamic diagram. And that's what some of you are doing. You're coming up with nice points, but then they're not actually, they're too specific. And you also have to make sure you don't lose any generalities either. In this case, it did say it was a right triangle. So I tucked it right into the x-axis to make my coordinates as easy as possible. If you can use zeros, that's great. So I've got one corner, it's going to be the origin itself. Here's this other corner at a comma 0. That means it's a point on the x-axis. And 0 comma b is a point on the y-axis. So this first proof works out pretty nice. And notice I can slide things around here. I can grab this point and move it around and see if our conclusion holds. The conclusion was that MB, MO, and MA, all these are congruent. And they're listed over here. There's D, you've got a color coordinate, that's 3.2. Distance, here's all the distances. Distance MA, MB, and MC, they all seem the same. No matter where I move these, I keep still getting the same distances for all those. Okay? Now, how do we go about proving this? This is not a proof. But it's a good idea so you know how to set up your problems. And that's sometimes a trick with this. I mean, it's nice if I've got everything labeled for you already, but often when you try to prove these, you have to come up with where things go. So let's go back now to here. Look at the proof now. In the proof, first I want to come up with the coordinates for this midpoint. And that's just the midpoint formula, A over 2, B over 2. Some people actually, when they set up their triangles, if they see a lot of midpoints, they'll start taking this and calling it 2A comma 0 and 0 comma 2B, just so the arithmetic gets nicer, so you don't have fractional expressions. But it still works out over here, right?
Right.
Yep. And now the distance MC, from M to C, the origin is just A over 2 minus 0 quantity squared plus B over 2 minus 0 quantity squared, which simplifies down to that. And now I can try the other one, MA, from A over 2 to A, which is A. So, but A over 2 minus A is negative A over 2, so we still get A squared over 4 there. So basically, these two expressions are equal, so MA equals MC. And we already knew MA was equal to MB. Why? Why is MA equal to MB? Yeah, that's one of the givens. It's given that M is the midpoint, so that divides that. Okay? Let's look at a slightly trickier problem here now. Prove that the median of a trapezoid is parallel to the bases and has lengths equal to the average of the base. Okay? How are we doing? Let's call it up in GeoGebra and just see if it all works out here. File, open, don't save that one. We want the new one. This is example 2. Here we go. You seem to have everything. I also color-coded this because now you've got a trapezoid. It really helps if you put one thing at the origin. That's going to save on all the numbers of letters you have to do and so forth. And also this really helps here too, that I've got a trapezoid, so I'm just going one of the parallel sides along the x-axis, making this also along the y-axis, right? So that's part of the given information. You're trying to show then that this midline is parallel to the other two. Well, let's jockey things around here. See that? This is a trapezoid. That Q is staying on that line. Here, R tends to bring Q along with it, but that's okay. It's just how I set it up. But we can come up with any kind of trapezoid we want. Doesn't have to be isosceles, right? Could be a parallelogram. That's technically not a trapezoid, but I think you'll find the rules still hold. If it's a parallelogram, what happens?
The other sides are parallel.
No, what's our theory?
That the
Notice here the purple ones. The purples average out to be 3.64. That's why I color-coded it.
right.
And is that equal to the length of MN, which is done up in blue here? Yeah, 3.64. So here I'm sort of experimentally checking the conclusion. And some of you were trying to just do that right away with specific numbers. You make sure they made the thing that was mentioned. But you have to do it for all possibilities. So that's why we're going to come up with general points for this.
Nice.
Okay? Notice what happens when you go to a parallelogram. It's still equal, right?
Right.
And what's happening, though, is now they're all equal. The midline is equal to the average of the other two, but these two sides in a parallelogram, opposite sides are congruent. Okay, that's just what it's doing. Now let's look at the proof. Proof. Where did you go? Right here. Again, we come up with the midpoints. First of all, does everybody see why I use B, comma C and D, comma C?
Yeah.
What do they have in common?
C.
C. Y equals C. So that's a horizontal line. It'll be parallel to Y equals 0, the x-axis. So that's, we've got our condition of having a trapezoid. Here's the conditions for the median, so we can just look at the midpoint with the midpoint formula. Prove now that MN is parallel to OP, this new line. Well, OP is just the x-axis. MN is this midline, and it gets a little complicated because they have to do the change in Y or change in X. But I get 0 over something that's not 0. I mean, I suppose I could write this as A plus D minus B over 2. How do I know that's not 0? How do I know that this is not equal to 0 on the bottom?
Because then.
Wait, what's B?
Because A plus D over 2 is the X coordinate of this midpoint, right?
Oh,
And B over 2 is the X coordinate of this one.
Not the same X.
So if their difference was 0, they would be the same thing. And you really wouldn't have trapezoid anymore. Okay. So that shows that those two are parallel. Now here's the distances. Oh, note, I am going to insist that you do this step. You don't just stop here. Show how your calculations connect to the geometric idea. Since, let's get this fixed up here. Since the slope of OP is equal to the slope of MN, that means OP is parallel to MN. Okay? All right. Here's the distances. Wow, the first distance is along the midlines here. And then the second distance is RQ plus OP over 2. So a lot of calculating here, but they both end up being the same thing. A plus D minus B over 2. So therefore, MN is equal to the average of the bases. Okay. All right. That's a nice proof. It's a little different than geometry proofs, right?
Yeah.
You're not really listing your reasons as you go because you're using these formulas that we've been using for coordinate geometry since Algebra 1. But now you're applying them to very generalized statements. Prove that the altitudes of a triangle meet in one point and that they are concurrent. The big thing I want to point out on this one is that setting up the triangle is a little different. Because notice I didn't put it at the origin like I did in the other ones. Let's open up example 3 now.
Say,
Where'd it go? It's back a page. Don't worry kids. We'll find it. There's example 3. Now, did I lose any generality? Because it just said the altitudes of a triangle. So, I don't know if it's a right triangle, I don't know if it's a scaling triangle. Is it general enough, though, to put 2 of the points on the x-axis and have the other one on the y-axis? Certainly you could do that with any triangle. It's got 3 sides. You can put one side on the x and then shift it around until that third point is somewhere on the line. And so now we can scooch these along. Oh, nice. And notice how the altitudes keep meeting the same spot. They're concurrent. Okay? We can move this over this way. Hello!
Oh my gosh.
That's crazy.
Even though it's called the orthocenter, it can actually be outside the triangle. Which is the lines point. Okay.
There you go.
Which of those concurrency things have to be inside the circle?
in center.
In center, because it's essentially the inscribed circle, so it better be inside. Circumcenter, no, sir.
Not the
No.
centroid.
Centroid, yes, because you're joining the medians. And those are segments. So, centroid's got to stay inside the inside. Flange point, orthocenter, and circumcenter could be outside.
What is a flange point?
Oh, I explained this to you many times.
Oh no.
No, it's
Is it
not
not?
I was in this video. That'd be
Yes, we'll look at it later, okay? Right now, let's get to the proof of this. Here comes the proof. Shh. People, we're still recording, okay? John has watched the microphone there very carefully,
It's on.
and it's still on. Okay, here's the proof. Got a lot of scribbles on my diagram here, because basically, it's tricky getting the equation of the perpendicular, the altitude to each. It's not the perpendicular bisector, so you have to use the point on the other side of the triangle and the slope of the current side. So the slope of this side, QP, is negative b over a, using these coordinates, a0 and 0b. That means the perpendicular slope is the negative reciprocal, or a over b, and I put that into the point slope formula to come up with the equation of the perpendicular line. And I do something similar over here. Then I take those 2 perpendicular lines, those 2 altitudes, and I cross them. Now I know all 3 are supposed to cross, but I'm going to cross these 2 and see if it's consistent with the third line. So y equals a over b. Oopsie. Back to my little point here. Y equals a over bx minus c, and y equals c over bx minus a. Set them equal. Multiply both sides by b. Distribute. A lot of kids freak out here when they get, they go ax equals cx, and then they divide the x's and they get a equals c. Is that what we're trying to prove? That a equals c?
No.
No.
That's
No.
not
So
what
you
we're
factor out the x and basically show them that x equals 0. And then you put 0 back into either of the equations, you get y equals negative ac over b. So that means we've got the intersection at 0, negative ac over b, which is on the y-axis. So that means all 3 altitudes are concurrent, because that was our third altitude, the y-axis itself. Okay. All right, that brings us to the homework problems. We talked about this already. The point of concurrency is called the orthocenter of the triangle. That brings us to the homework problems. Figure OPQR is an isosceles trapezoid with OP equal to QR. Prove that OQ equals PR. This one was a little trickier to set up on GeoGebra, and I encourage you to try setting up some of these things on GeoGebra so that you can see how the conclusion is coming about. And you can try a bunch of different points on it and so forth. So let's call up this one now. Open, what would you call it? Where'd it go? Where'd all our options go? Did I hit save instead of open?
No, you.
PCH, right? PCH. You know, I think I tried to save it. Let's open a new one. Open. Don't save. Right. I think I might have hit save on there. Michael, focus.
Oh,
Here we go. Here we go. Homework problem from 6 point. There it is. Bingo. So I really encourage you as you're setting these up, if you volunteer to do some of these, to get on GeoGebra. I'm going to insist on that. If you're going to try and take on one of these for homework. Okay. Here's our isosceles trapezoid. Notice I have B comma C here. I didn't mention what Q is yet. Is it truly dynamic? Oh, yes. Now, that's a problem. That's not a trapezoid. Trapezoids only have one pair of parallel sides. It has to do with how I set up Q. I set up Q. I had two choices for Q. And notice I can't seem to move Q because now Q is forced. Because for an isosceles trapezoid, you've got to get these side things equal. The bases don't have to be equal, they just have to be parallel, but these ends have to be equal. Okay? All right. Now you did a lot of proofs for this, the little butterfly triangle effect. Remember that in geometry?
Yeah.
You come up with why these diagonals are congruent. You kind of remember that?
Oh, yeah.
Because you've got these triangles, and because of the parallel lines, you get a bunch of angles congruent and so forth.
Oh, yeah.
Yeah. Very elegant proof in geometry. Let's get to the brute fortness of it all. Here we go. Here's your coordinate proof. Wow. The trickiest part is coming up with the coordinates for Q. It's on this horizontal line because we want to make this horizontal match with that, so that's why it's a coordinate of C. Where is A minus B coming from for the X coordinate?
It's like it's A over, but then you have to like subtract the B because like you can bring it over and then
To make it match this triangle.
yeah.
Okay. Notice how in these two triangles, they both have this side. So you're going to have to go over, you're going over B and up A. So we have to back up B and go up A to get it to match over here. So that's why you have A minus B over there. Okay? So QB or OQ, there's the formula. Now you don't have to spend a lot of time simplifying as long as you can get them to agree. Because you might say, wasn't there a way to simplify this? Well, it doesn't matter because when I did RP, I was able to get them to be exactly the same expression. Therefore, QO equals RP. All right? Well, just in time for the end of class then. All right. So people,
Flash out!
there you go. Say it with me now.
Flash